crazy.
You get it? I will begin with a word of prayer. Heavenly Father, we thank you for this day again, Lord. I thank you for the students. Just ask you to just bless this class. Help us to just understand a little bit more about your creation, about how to understand minimums and maximums and so forth. And just help the students, if they're not doing as well as they want, just to encourage them to persevere and just to keep on and just do the best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. Yeah, so, not so good this second test, but, well, there's always a third and a fourth test, right? So, optimization is our next topic. And so, of course, of functions of several variables. And so this is an interesting topic, of course. One that comes up if you apply math to your daily life, if you're working for industry or whatever. You have some function that describes some physical process. Maybe you want to find how to minimize or maximize that output, right? This is the kind of math you need to do to understand that, at least for continuous problems. And so here's generically the setup. We've got some function, right? Some function which is defined on the domain of f, all right? Which is, let's say, some subset of Rn, and it's going to the reals. So for us, we'll usually look at n equals to 2 or 3 for the most part. But I'll tell you some things that are good for 4 or more dimensions. And the question is, for a given domain, right, for a function defined on some given domain, how do you figure out where the function's largest and where it's smallest, if that's even possible, right? So here's kind of a generic picture of what's going to go on. So the domain of the function, it can look like all kinds of crazy stuff. I don't know, whatever. Maybe this is the domain of the function. The point is, the domain of the function, well, it doesn't have to look like this, right? The domain of the function could also just look like this, right? I mean, it could be you had a hole, right? And then the domain of the function is everything outside that hole. I mean, there's various possibilities you could think about, right? The domain could look like that. Over here, I tried to make the domain look more like that. Now, the domain on the left is what I would say is a compact domain. Compact in the sense that it's closed and it's bounded. Closed means that it contains all its boundary points. So I illustrated that by drawing the solid edge. All right, so what are the boundary points? So if I said the domain of f was equal to u, just to give a language here, then the boundary points, like here, this point P is an element of what we call the boundary of u. So we use a partial on u. That's notation for the boundary of u, okay? That's not a differentiation. It's just another cute use of the notation, all right? The cuteness is understood later in the course, so you'll forgive me for not really explaining why on earth we're putting that symbol there. But nevertheless, this is a standard notation, the boundary of a set, partial of a set. So the boundary here, so this, in my picture, the u, right, the interior of the set, it's basically an open two-dimensional space, right? It's an open two-dimensional set. You have the interior and you have the boundary. So this boundary is basically like a one-dimensional curve, right? And the interior is two-dimensional. And so if we were given such a function with such an interesting domain, it turns out we have to divide our thought process into, here's the big picture of what we have to do. To optimize such f, number one, you have to find where f has local mins and max within the domain of f, right, within u. So what would a local min or max be? Like, for the sake of discussion, it could be that this point right here, if this point P was if this corresponded to if this was a local max, what would that mean? What that would mean is I could find some like little open disk around there, right? I could find some like little open disk, like this, right? Such that if we take f and restrict it to the disk, right? Any point in that disk, that's going to be, if it's a local max, that means what? That means that f of p is bigger, right? It's bigger than anything else close to that point. So we'd say I could just say this, f of x is less than or equal to f of p for all x near p. And what I mean by near p is that there exists some open disk so that if we evaluate the function on that open disk near the point, then the value the function takes at that point, well, it's the biggest, right? Or at least that value is not surpassed in that local neighborhood, yeah.
If f of x can be equal to f of p for that to be true, can you just have a completely flat surface?
That's true. If we had a constant function, then it would everywhere have a local maximum. It would also everywhere have a local minimum. See, because the other side of this is if I have a q, right, and this is a local min, if q is a local if q is where there's a local min for the function, that would mean that f of x is less than or equal to f of q for x near q. Now, I say x near q. If you want to make that more formal, you could say for all x, there exists epsilon greater than 0 such that the disk of radius epsilon centered at q, if we feed the function inputs from such a disk, then the outputs are at most f of q. Did I just make it the same again? Yeah, I'll do that. This is why I shouldn't teach real analysis. Well, this is why I should be watched carefully while teaching real analysis. All right, so that's supposed to be obviously that, but you guys already knew that, so. So my intentional pedagogical mistake was successful. Yes. All right. Did you enjoy the interaction? That's classroom interaction right there. That's good. All right. So number one, we have to find where f has a local minimum or maximum in the interior of the domain. Step number one. Step number two, in the big picture of things, is we have to find where f is, minimized or maximized on the boundary of the domain, right? See, because the local mins or maxes, we're not going to pick up on local min. If the minimum or maximum was on the edge, we wouldn't even consider that in our local min-max considerations. So we have to think about the edge separately. If there is an edge, all right? But if there is an edge, we have to think about that separately. So we have to evaluate the function on the boundary and study the min-max there. And then step three is, well, just analyze 1 and 2, pick your winners and losers, right? Right? Now, I will tell you, there's a theorem which says that, here's a theorem that I should tell you before we even start. This theorem comes to you from a branch of mathematics called topology. The theorem says the following. If the domain of f, right, a subset of Rn, is compact, and f is continuous, then f attains min and max values at least once on the domain of f. And here again, f is a mapping from some subset of Rn to R. This theorem that I'm telling you right now, this is the so-called extreme value theorem. You've already seen this theorem at play in your Calculus 1 course. Do you remember the closed set test? So we take a closed interval, right? And then we look at a continuous function. We had a theorem which said, it was called the extreme value theorem. It said that the function attains a minimum and a maximum value if we feed it inputs from the closed interval. And you may recall the closed set test. What did we do? We checked the interior of the closed interval to look for local mins and maxes, and then we had to check the endpoints. That was the boundary, and then we select winners and losers. Well, the same thing for multivariate functions. It's just now, instead of looking at a closed interval, which has the boundary just being 2 points, well, when we have a set which is two-dimensional, the boundary can be a curve. If our set was three-dimensional, the boundary could be the surface, the bounding surface to the volume, and so forth. All right? Now, there's something you guys should ask me. I used a word. What word did I just use? Compact. What does compact mean? It's like something you put your makeup on with? No. What is it? Sorry. Oh, I forget. I'm trying to reach out to the FACS majors in here, taking Calculus 3. Not really. No. Okay, well, just checking. And there could be a double major. I mean, there's got to be a double major in math and family and what's FA's? What's it stand for? It's family and consumer science, right? Why there should be a double major in math and that, right? Why not? It could happen. It's possible, right? What? Worlds colliding? I don't know. So this term compact for you guys, what that means is closed and bounded. So that's what compact means inside Rn, closed and bounded. So closed means it doesn't have a fuzzy edge. What does bounded mean? It's not from infinity to negative infinity. That's kind of the right idea, fuzzy. Here's a precise statement of it. You can find an open disk that is big enough that the whole set fits inside that open disk. If you can do that, it's bounded. If you can't, it's not. This guy over here is not bounded. I don't think it's closed either. It doesn't contain its boundary points, right? Like the boundary points in the whole, they're not in the set, so this is actually not a closed set. So what I'm trying to tell you, the big picture, we're going to study optimizations of functions, right? So context is key. What are you expecting? Well, I'm telling you that there's this wonderful, well-known theorem of topology, which we're not going to prove, but we're going to use. All right? This is going to help us know what we're doing. Yeah.
Just going back to what you said.
Go for it.
Even if the boundary points of that whole were included in the set, wouldn't it still be not bounded because it goes on forever?
Right. If it included the boundary points, it would at least be closed, but it still wouldn't be compact because it's not bounded, right? I can't take a disk and a finite disk and put it in there. So here's the rub. If we have a function whose domain is not compact, even if the function's continuous, we don't get the extreme value theorem. All right? It's fairly easy to come up with examples of functions which do not have a global minimum or maximum. So this 3, what we're picking here in part 3 is the global extrema. Extrema, global, or extrema, however you want to say that. But the global extremes, the mins and maxes, that's for the whole set, right? For the boundary and for the interior. Those may or may not exist for a function where the domain is not compact. Let me give you an example of that. How about this? If we look at f of xy equal to e to the minus x squared minus y squared, right? And by the way, if I was so foolish as to attempt a picture of this, we could look at this as a graph, right? We could look at the graph to understand what I'm saying here more geometrically as well, right? Like a local max would be sort of like a tent, right? And the tent pole would be at the maximum. And a local min would be sort of like a dip. Whatever you want to call it. What would that be called? I don't know, a sink? We have a word for that. A hole. The Q is the bottom of the hole. A hole, yeah. Trench, something like that. What's that?
Abyss.
An abyss.
Less for the global, I suppose.
Okay, so this function here, I can graph this, right? In fact, this function's even nicer if we just put it in terms of polar coordinates, right? This is really just what? F of r equals to e to the minus r squared, right? So if you were to plot r this way, in fact, we should really only plot r that way. Hey, r is non-negative, yeah? It starts at 1, and it just kind of like that. So that's the plot for any theta, right? This function is independent of theta. So basically, you just take that and rotate it around the z-axis. That's the function. If I can foolishly attempt a plot of it. Although I think the top is actually not jagged. I think it's smooth, I believe. There's my foolish attempt at a picture of this function. Anyway, you can, what's the global maximum? And I'm claiming that I know what it is just from basic function, like pre-calculus, really. Think about putting an input into the exponential. We're looking at minus, I mean, this is really what, exponential? By the way, I use this notation sometimes, guys. That's just the same as this. It's just helpful for me to write it in a different font, basically. So we're taking exponential of something that's negative, right? Yeah, what does the exponential function look like? Just think about e to the x as this, right? Let me make this u. And here, basically, I'm plotting e to the u, right? So think of this as being u, right? So u equal to 0, it's 1, right? And as x and y increase, as the radius increases, we're just getting more and more negative exponential. In other words, we're kind of like value-wise going like that, right? So the picture is, I'm trying to make my picture is not right. It doesn't come up here, right? It does, it's more like, I still can't. See if I can attempt this again here. So it goes asymptotically to like the x and y axes along the yz plane or the xz plane, right? Let me make this dotted. Oops. Try that again. Anyway, so then that just goes on out, right? And it's symmetric about the origin. It's just kind of like an infinite tent with the pole on the z-axis at where? At 0, 0, 1, right? This point right here. So I think you can see that f of 0, 0, right, which is equal to 1, is greater than or equal to, you know, e to the minus x squared minus y squared, right? For all xy in the plane, right? The whole plane is not compact, right? If you want to be technical, it is technically closed, but it's certainly not bounded, right? So there's its global maximum, 1. We didn't need calculus to figure this out. We just thought about the function and worked out the pre-calculus of it, really, right? What's its global minimum? It doesn't have one. What would like to be its global minimum?
0.
Yeah, so 0 is a bound below. I mean, you really can't improve on this. 0 is strictly less than e to the minus x squared minus y squared, which is less than or equal to 1. I mean, we have that inequality from just essentially the exponential function's properties in common sense. Or perhaps uncommon sense. I don't know. Anyway, so not compact. There's a global maximum, but not a global minimum. Nevertheless, the function is bounded below by 0. So there's an example. Of course, you could have other things, right? Here's an easier one. we could look at f of x comma y equal to x squared plus y squared. Right? So if I look at the graph of that, we've done this several times. That's not quite right, but you get the idea. Here's my z, here's my x, here's my y. It's fairly clear that the global minimum of this function is what? Yeah, it's at 0, right? F of 0, 0 is equal to 0. And you can see that 0 is less than or equal to x squared plus y squared, right? And of course, that's f of x, y, right? And that's true for any x and y. So in fact, 0 is the minimum value. It is attained at the origin, and that's a global minimum. Is there a global maximum? There is not. What's the domain of this function? It's the plane again, right? So it's not compact, so it goes on and on. All right. What if I did something? What if I said, let's add some fine print here. What if I made the domain compact? How could I do that? Easy enough, right? Suppose that x and y are the number of widgets in stock, and we count negative for pre-orders, right? It then it could be possible for a given factory that we had to have x and y between, say, 10, and to make things easier, x squared plus y squared. It's not right either. Oh, stink. Yeah, suppose x has to be between 0 and 10, between 10 and plus and minus 10, and suppose y had to be between plus and minus 12, I don't know. Then all of a sudden, you're just looking at, x going from 10, that's your new domain, right? And so it's just going to kind of like, yeah, I can't even draw it. There's some kind of everything, there's just this part of the graph to play with now. So the global minimum is going to be 0, 0, right? And the global maximum, since I made with that, the domain is actually just if I draw the domain, it's just a rectangle, which is compact, right? Because it's a finite. If it's a finite shape with not fuzzy edges, it's just compact. So the extreme value theorem would say that function attains a maximum somewhere for that range of inputs, right? How would we find the maximum? That's the question we're trying to ask right now and answer, figure out a way to do that, all right? Actually, that's not really the question I'm interested in. This is just messy. Here's a more fun question. Instead of that, you could say, say f of xy equal to x squared plus y squared on 0 less than or equal to x squared plus y squared less than or equal to, I don't know, something like 3x squared. Less than or equal to, I'm still not doing it justice, guys. Let me draw a picture with the domain of f looking like this. So the ellipse that you guys just had fun playing with on the test, right? So this guy, x squared, or something like it anyway, x squared over 9 plus y squared over 4 equals to 1, right? Suppose that this is the allowed inputs to f, right? There's your domain of f. Find the minimum and maximum of that f on that oval. Can you guys tell me what it is? Okay, good. Then we need a method. All right, so this is the big picture. This is what we're doing. Let me tell you where we're going. We're going to spend the rest of today talking about point number 2, actually. Point number 2 is where I'm going to start. I'm going to describe a method to find mins and maxes on the boundaries of sets. This is called the method of Lagrange multipliers. All right? That method is supplemented with another less kind of interesting method, which is just you find a parameterization of the edge and just plug it in and work on that. So either Lagrange multipliers or you just explicitly like restrict the function to the edge and work on it. We'll see that Monday, where we talk about the closed set test, which has that in it. Now, tomorrow, we're not meeting, right? But I'll send you a link to the video from last year where I derive I introduce power series and several variables in that. The last 30 minutes of it, I look at power series. And the first 20 minutes of it, I do a very sort of interesting Lagrange multiplier example, which is kind of an uber example. I use that example to build what's called the second derivative test. So just to give you a long story short, we'll eventually get back to point number 1. I mean, I can tell you how we do it in a nutshell. We find critical points, and then we check whether those critical points are min-max with the second derivative test. That's how we do it. However, we also have the multivariate Taylor theorem to work with, and that gives us added insights when the second derivative test fails. Then point number 2, we're dealing with today with method of Lagrange multipliers. And then point number 3 is what we come back to in the end, right, when we put all these methods together. That's the big picture. All right. So, yes, sir. Attendance. Curses. Josh has it permanently. He's devoted a page. He doesn't write it every class. He already has it like big on a certain page. He just flips that open and puts it up. It's like he's prepared. It's here. It's good. For some reason I have sticky notes on this. Come on. There we go. You could add the date, whatever the date is. Okay, so method of Lagrange multipliers. So here's the problem. You're given what's called an objective function. Let's say f of x comma y. I'll do it three-dimensional because it's more interesting that way. F of x, y, z. Given an objective function, f of x, y, z, or it could be two-dimensional, f of x, y. All right. I guess it could have more, and you're given a constraint. All right, so the constraint is either something like g of x, y, z equal to a constant, or g of x, y equals to a constant. Now, so in other words, we're either going to look at a function of 3 variables, all right, and try to figure out where is it largest or smallest on a surface, right? So this would be a constraint surface. Or we're going to look at a function of 2 variables, and we're going to ask the question, where is this f of x, y largest on a constraint curve? All right? And the way this works is we assume that there is a minimum or maximum defined. All right, that's the starting idea for the derivation here. So I'll work it out here. So I tell you what, I'll let you guys pick. Do you want me to look at the? I'm going to look at the surface one just because the pictures are more interesting. Okay. But the derivation works almost the same for 2 dimensions. So the idea here, right, is we can look at. Here's, the constraint surface, g of x, y, z equals to a constant, right? And what we want to do is we want to assume somewhere on that constraint surface, the objective function attains an extremal point. It's either minimized or maximized. Tell you what, let's assume it's maximized just for the sake of discussion. All right, so you guys be more comfortable with the discussion. So let's suppose that f of p is, local max. There, right there. So if that's if that point on the constraint surface, right, is the point where f attains a maximum, what can you tell me about, what does that mean? That means that if we look at paths, right, if we look at paths that pass through P, right, then what can we say about those paths? Like this one, for example. Suppose this is, R is a mapping from, I don't know, let's say the reals to the, the constraint surface, which I probably should give a name. What do you guys want to call this constraint surface?
Pac-Man.
Pac-Man? All right. Let the record show that was Nathaniel's choice. All right. So, suppose you've got a path onto the Pac-Man surface, right? So that would mean what? And we can suppose that R of 0 is equal to P without loss of generality. So we have the following. We have that G of R of T, right, is equal to that constant C, whatever it is. That's what it means for that path to be on the constraint surface, right? But on the other hand, you can think of another thing, right? You can think of h of t. We can think about h of t being what? H of t could be f of r of t. I can think about taking that same path, right? And I can evaluate the function at the path, the objective function, not pictured, by the way. And what should you know? What should we be able to say about h of 0? What is h of 0? H of 0 is f of r of 0, which is by construction what? F of p, which is what? Local max in my current discussion, but so this new function h I just invented, apparently t equals to 0 is where it also picks up a maximum, right? I mean, if you constrain the objective function to sort through value, like here's a typical R of t right there, right? If you trace out the curve, feed it to the function, the objective function, which takes a max at p, then when we look at t equal to 0, that gives us a maximum for the h of t. What's that? And so if we assume that f is differentiable, and if we assume that this is a smooth path, that means that h is a differentiable function. So what did we learn in Calculus 1 about if h has a local maximum at 0, then what should we say about the derivative at 0, given that it exists? What do we have? What's that? It's 0, right? H of 0 max implies h prime of 0 is 0. All right. Now let's put it together. So the fact that the path is on the Pac-Man surface, we've looked at this before, right? If we differentiate this, what does it give us? Differentiating with respect to t gives me what? It gives me that the gradient of g, evaluated at r of t, dotted with the velocity vector to the path, is equal to 0, right? And how about the h? If I differentiate h, take star, differentiate it. We got dh dt, right, is the gradient of f at r of t, dotted with dr dt, right? So setting t equals to 0 gives us what? Then we get 0 is equal to the gradient of f at the point P, right, dotted with dr dt at time 0, right? Now, of course, you can, the gradient vector field to G is always perpendicular to the surface, and it's always perpendicular to tangent vectors to the curve at each point, right? That special point P, where the maximum is, well, it's perpendicular. And there we can also compare, at this extremal point at P, we have two things, right? On the one hand, I mean, by the way, if we just take, let me call this thing star star. Star star, also set t equal to 0 gives me what? It gives me 0 is equal to the gradient of G at P dot dr dt. So if we were to plot dr dt, the tangent vector to the curve I pictured, it might look like this, right? So we know what the gradient of the level surface looks like. It's perpendicular, right? I mean, we've talked about that. But what about the gradient of f? The gradient of the objective function, where does it have to be? If it's perpendicular to the velocity, you know, it has to be what? I mean, where's the gradient of f look like in this picture? I don't think you can say just yet. The thing is, so I mean, logically speaking, right? Here's the choices. If this is the velocity vector, right? Well, then sure, the gradient of g has to be there, right? Just looking at this one curve, the gradient of the objective function could be like any of these directions, right? Those would still be perpendicular to the velocity, right? So, but here's where the thing gets more interesting is this calculation we just did is good not just for one curve through the extremal point, but for all possible curves through the extremal point. So, you know, you could picture a different curve, say R2 of t, which had a different tangent vector like this one, right? And again, you'd still need, you know, I then need that, well, the gradient of g is still perpendicular, right? But I also need that the objective function, the gradient of f, has to be perpendicular to that velocity, right? And so you start sorting through this. It forces you to make the gradient of f to be in the same, along the same line as the gradient of g. That's the only way we can get perpendicularity to all possible tangents in the plane, is if the gradient of f looks like this, basically. Or it could be like this. This is also possible. I don't know. So the gradient of f has to point along the same line as the gradient of g in order to get both of those conditions. And this is the method of Lagrange multipliers. It simply says that at an extremal point, the gradient of the objective function should be some scalar lambda times the gradient of the constraint function. That is the method of Lagrange multipliers. It says that there's some multiplier, lambda, that's the Lagrange multiplier. This is a constant. There has to be some constant such that the normal to the objective function is simply a scalar multiple of the normal of the gradient to the constraint function. They have to line up in this way at the extremal point. So this gives us a way to search for extremal points. We just look for where that boxed equation is met for a given problem. All right? Now, almost the same calculation goes through in 2 dimensions. It's just instead of thinking about a level surface, we think about a level curve. But essentially the same calculation shows you that you also have that condition in 2 dimensions. All right? So let me do that here. So let's try method of Lagrange multipliers on my example right here. So let's try to find min-max. Now, I think by the time we get to the end of this problem, you'll be like, well, that was dumb. I didn't need calculus for this. I shouldn't even say that right now. I shouldn't say that. So here, so basically I'm saying x squared over 9 plus y squared over 4 equals to 1. Find min-max of f equal to x squared plus y squared on this curve. Okay. So the method of Lagrange multipliers, how does it work? We calculate the gradient. So first of all, I have to identify my constraint, which is this. There's my g. So I'm supposed to look at the gradient of the objective function equals to lambda times the gradient of the constraint, in this case curve, level function for the curve. So you guys can calculate gradients, mostly. Let's see here, so 2x, 2y, lambda, what we got here? 2/9 x, yeah? And looks like we got ourselves a 2/4 y. So what's this say? This says that 2x is equal to lambda times 2x over 9. And it says that 2y is equal to lambda times 2y over 4. So let's get rid of these 2's. You know, let me just clean this up a bit. This says that x is equal to 1/9 lambda x. And this says that y is equal to 1/4 lambda y. Now some of you are like, just cancel the x. Well, okay. If you do that, that comes with strings attached, right? Canceling x says what? X is not 0, right? So, I mean, how do you want to deal with this? So we got to solve, basically the problem is to solve this, and one other thing, x squared over 9 plus y squared over 4 equals to 1. This is the problem of Lagrange multipliers. We have to solve these. And that's most of the pain and suffering for you guys, all right? New algebra. This is algebra you never learned in Algebra 2 or 1, right? You remember the test where you learned how to solve like three nonlinear equations which are coupled? You shouldn't remember that. You didn't do it, okay? So this is new algebra, but you can use the things you already know about algebra to solve this, but you must be careful, right? If you divide by something, you have just assumed it's not 0. So you have to break that up into a separate case. Let's work through this. Let's see how that goes. Let's try that out. X equals to 0. If x equals to 0, right? If x equals to 0, then what? The third equation's super nice, right? Y squared over 4 is equal to 2. So y squared is equal to 4, which gives me what? Y is equal to plus or minus 2. So we find 0, 2, and also 0, minus 2 as candidates. In other words, candidates for min. Yes?
How do you get equals to?
Yeah, where did the 2 come from there? Isn't that 1?
That's a 1.
But then you did math like it was 1.
Yes, it was 1 in my mind, but not in my marker. Not cool. Thank you. I'm sorry, that was on purpose. I'm glad you were paying attention. Very good. All right, yes. Anyway, so there's 2 possible solutions. And then, so what else? What's the other choice? X not equal to 0, right? If x is not equal to 0, then the x equals to 1/9 lambda x implies what? 1 is equal to lambda over 9. So lambda apparently is 9. You're like, so lambda's 9. But we're not looking for lambda, right? Lambda's a tool. Lambda's a device to finding the answer. It's not what we're actually interested in. But that's fine. If lambda's 9, then what's that tell us down here? Y is equal to 9/4 y. So where I come from, that says that y is 0. All right? So that has solution 0. But if y is 0, go back to the third equation. What does x have to be? X squared over 9 is equal to 1, uno, which, of course, implies that x squared is equal to 9, which then tells us that x is equal to plus or minus 3. So we find 2 more solutions, 2 more candidates, right? What are the candidates? Looks like we got ourselves a 3, 0 and minus 3, 0. So these are the 4 solutions to the Lagrange multiplier equations for this problem. All right, so the method of Lagrange multipliers, I really haven't fully written down anywhere yet. Let me do that. So here's the method of Lagrange multipliers. Number 1, you got to identify your objective function f and your constraint function g, right? Step number 2, you set up the gradient of f equal to lambda times the gradient of g. For the problems I'll give you, you can do this. If you take advanced calculus with me, I will show you that this is just the start of a story which is more lengthy. There are problems which require more than one multiplier because there's more than one way. I mean, anyway, so you can have multiple multipliers, but not for the problems you'll see in here, okay? I'm just telling you, this is the most naive method, naive chapter of the method that we're teaching you in here. It's the start of something more general. Take advanced calculus if you want to see more, but anyway, so we set up the Lagrange multiplier equation, and then 3, you solve gradient of f equal to lambda gradient of g with simultaneously, this is important, simultaneously with your given constraint equation. You notice we did that, right? That's what I was doing over here. I set it up. I boxed the 3 equations. The top 2 are my Lagrange multiplier equations. The third one is the constraint equation. You notice to actually work this out, I had to use the constraint equation, right? That was an integral part of the thought process. And then step 4. Step 4, pick min-max from solutions to 3. Beware. If G equals to C non-compact, then anything can happen. if your constraint curve or if your constraint surface is not a compact thing, we don't get the extreme value theorem, garbage in, garbage out. So the assumption of the derivation was that there exists an extremal point. If your constraint surface or curve is not compact, well, you're looking for something that's not there. I mean, you can go through the steps, but it's deceiving. So what I'm trying to say is the method of Lagrange multipliers is applied to things which are not compact in applications lots of times. But when you have your constraint not being compact, you got to use some common sense and some extra thinking to sort through your answers and make sure you're not getting fooled by the method. Lagrange multipliers gives us possible places where we find mins or maxes. They're not necessarily places with mins and maxes if the constraint curve or surface is not compact. Now this one, is this compact? Yeah, this one's compact. So we're gonna find answers, right? So let's do my step 4 over here. We got to look at f, and I'll just combine them. F of 0 plus or minus 2, and you can look at f of plus or minus 3 comma 0. What are those equal to? You got yourself a 4. You got yourself a 9, right? Because remember, f is x squared plus y squared. And at this point, you may regret your life for doing all this calculus because it might become obvious to you why these answers are what they are. What is my objective function? What is this? Geometrically, what is that? What? No. What is the function? F of x equals x squared plus y squared as it relates to the geometry of the plane. No, setting equal to a constant is a circle. What is x squared plus y squared as it relates to the geometry of the plane? I give you x comma y. I tell you, here's x squared plus y squared. What is that? I give you the square root of x squared plus y squared. What is that? Right? That's the distance. What is x squared plus y squared? It's the square of the distance. It's the distance squared function, right? So really, the question we're asking from the origin, right? So we're asking the question, what's the closest and furthest points on the ellipse with semi-major and semi-minor axes is pictured relative to the origin? Of course, those points, if I could draw it right, are this and that, right? These are the points that are furthest squared distance, namely 9, and these have smallest squared distance, namely 4. So the answer is, if I did my picture backwards? No, it's right. So, I mean, so sometimes, although honestly guys, I have assigned exactly this question on tests before and still have students not notice that and like still get, I don't know, I'll always have like a token student or two who just doesn't do calculus and just says, answer, you know, and I can respect that. Unless, of course, I've written those dreaded words in the problem statement, which I try to write, use calculus to find the minimum and maximum. You say, well, that's not a nice problem to use calculus on because you don't need to use calculus. Well, that's exactly why it's a nice problem, is because you don't need to use calculus. That makes the problem nicer. Yeah.
So for step 4, because we got those outputs, do we just look and say like, oh, well then 0 plus minus 2, and those points must be the minimums?
Yeah, this is the.
Less than 2 choices?
That's the min. That's the max. So the maximum, which is attained, 2 points, right? At minus 3, 0 and 3, 0. And likewise, the 0, 2 and 0, minus 2 are the points at which the minimum is attained.
Will we only have 2 like that for the...
Oh, it depends on the example. It totally depends on the example. There could be 10. Here, let's look at a different example. if I can. Yeah. So I have some examples in the notes where I actually look at something, like I think I have an example in the notes where the constraint curve is the hyperbola. And if you look at like the constraint curve being a hyperbola, and then you take your objective function to be like x, if you solve the Lagrange equations, they'll give you solutions, but they're just total nonsense, because if you look at the x on a hyperbola which opens sideways, right? It gets arbitrarily negative as you go that way. It gets arbitrarily positive as you go this way. And yet the Lagrange multiplier equations will give you like the vertex points for the hyperbola. I mean, you can kind of see that. If we look at this hyperbola, right? So if that's my g, what would that be? Do I want x squared minus y squared equals to 1? Or do I want the other way? I heard a yes. Let me see if I agree with you. If we put x equals to 0, we get minus y squared equals to 1, which has no real solution. Bingo. This curve does not cross the x equal to 0 axis, aka the y-axis. Yeah. And so if you look at your objective function being x, right? Well, what's the gradient of f look like? It's x hat, right? So when you solve the equation, lambda times the gradient of g equal to the gradient of f, when is this going to have a solution? Here and here, right? So you'll get this and this as places where the objective function is ostensibly minimized and maximized. And you could trick yourself into thinking that minus 1 is the minimum and 1 is the maximum for x on the hyperbola. And you'd be so very, very wrong. Right? So method of Lagrange multipliers is only safe for compact curves. I mean, because what values does x take on the hyperbola? Anything outside of 1 and minus 1, right? 2, minus 27, whatever. Let's look at a more interesting problem. How about this? Suppose you wish to inscribe a rectangular solid in the sphere x squared plus y squared plus z squared equals to 1 of maximum volume. So what's the maximum volume rectangular solid you can inscribe in the sphere? A cube. Yeah, you guys already know the answer. Dang it. But if I spoil it, it's going to make the math much harder. So just bear with me here. Actually, I can't draw the picture worth anything. Well, let me just play with this for a minute here. You guys already told me the answer, so it's kind of demoralizing me, but I'll deal. So z, x, y, right? And so I want to, let's see here. I'm trying to think how to picture this. Oh, I guess I just have to face that this is outside. I mean, let me do something I can actually draw in class today. Let's do a rectangle. Rectangle in the disk. Yeah. Get rid of that pesky z. Oh man, it's another two-dimensional example. That's no fun. Max.